Okay, now let's do a design example of a beam determining the moment capacity of a beam with known quantities. So we have a W24 by 62 with a yield stress of 50 KSI, an unbraced length of 8, and a CB of 1.0. We're going to assume bending about the major axis, so the x-axis. First, we're going to do, there's two ways to do this. Not first, but there's two ways to do this. You can be an overachiever. And use the equation in the spec. All right, all those long equations, you can calculate the yielding moment, you can calculate its lateral torsional buckling capacity, and calculate what's going to happen. But the easier way to do it is to use the design tables. So that's what we're going to do. This is easier. And we are engineers. We are all about efficiency and ease. So you know those design tables are right. Somebody checked that a few times. So let's just use them. So let's see, a reminder, we have a W24 by 62. A yield stress of 50 KSI. Now remember, the only reason we can use these design tables is because of the assumptions that 50 KSI yield stress and a CB value of 1. If those two things weren't true, we couldn't use our design tables. Actually, I think if the CB was not equal to 1, we could use the design tables because it's built in there in the equation. So, actually, I'm lying right now. And an unbraced length of 8 feet. Okay, so I'm going to go to table 3-2. Let's see. And look for a W24 by 62. Let's see. There it is at the top of page 3-25. Let's see. I go across and I find my length associated with my maximum plastic moment. LP is 4.87 feet. LR, where I begin to have inelastic lateral torsional buckling, is 14.4 feet. My 8 feet is in between them. So I get to use that equation that I just used before. This means that I am in inelastic lateral torsional buckling. Right? That is the that is the mode of failure. The limit state. That's the word I'm looking for. Limit state. So I get to use that equation that I used before. That equation can be found on page 3-10. It's equation 3-4A. And I know everything. Let's see. Well, I always know everything. But I want to make sure I need to know my phi, right? If I go back to page 3-25, my maximum plastic moment for a 24/62 is 382 kip feet. And my little interpolation factor, Phoebe BF, sounds like Phoebe Buffet. You guys are way too young to know what Friends is, but it was a show back in the day. 24.1 kips. Okay. Substitute all my values in there. $382 kip feet minus 24.1 kips times 8 feet minus 4.87 feet. My capacity, as long as it's less than my maximum plastic moment. Wait, 24/62. Right, 574. I wrote down 382 because that is the wrong one. It is 574. I hope somebody caught that before just now. The 382 was our ASD value. It's 574. I actually have the numbers written down here, but you know, I'm doing it as I go, just along for the ride. And the number that I got was not anywhere near what I had before. So I got 499. Let's rewrite that. That's less than that 574. So if I want to know what my flexural capacity of a 24/62 with FY 50 and an unbraced length of 8, assuming a CB of 1 and major axis bending, I can hold just under 500 kip feet. have a bunch of blanks in here because sometimes I write big. So I will delete those. So the question is, what if I don't have a CB of 1, okay? So far I've been assuming that okay, so that was my example for finding a capacity. I have another example after this that we can all do together, doing basically the same thing as here. So if I don't have a CB equal to 1, well, I go back and look at my spec for flexure. And this is my equation. That's chapter J. That's the wrong chapter. Flexure, here we go. Equation F-F2-2. I have my CB factor in there, right? A reminder, my CB factor is that's not how you write that. Account. Golly gee, let me write that better. To account for non-uniform moment along the length of the beam. Right? If I have CB equal to 1, then it's a uniform moment. CB greater than 1 is for a non-uniform moment, and CB equal to 1 is actually right. More conservative. But let's say I'm really close and I'm like, I'm going to incorporate it. So this is my equation. Let's say I want to find my phi b mn, and I'll add another phi b right here. Basically, I can take that part out. This part right here, everything from the bracket on, would be my mn, if I have that phi b in there, right? Would be my phi b mn if my CB was equal to 1, I just crossed it out, right? So basically from the design tables give me phi b mn assuming CB is equal to 1. So if I go to my design tables, or charts, all I have to do is multiply my phi b mn by that CB factor, provided phi b mn times that CB is less than or equal to my plastic moment, right? I have to stay below that plastic moment capacity. But if my CB factor is 1.1, and I have a 500 kip foot capacity, or I'm sorry, yeah. If I have a 500 kip foot capacity and my, right? Let's say assuming CB is equal to 1, but let's say CB is equal to 1.1. Well, I can, 1.1. I can just multiply that. Now my capacity is 1.1 times 500, 550 kip feet. If I'm assuming I don't have a non-uniform moment distribution along the length, I can get another 50 kip feet out of it, right? That's 500 times 1.1. Yeah. But if my MP, let's say that was 525, well, knocking that back down, now I can only get 525 kip feet. So I can get another 25 kip feet out of my capacity if I make an assumption of a CB greater than 1, but it's not as much as I want because I'm always limited by that moment. Always limited by your moment, your plastic moment capacity. Right? That's just, if I read something from the design table, I can just multiply by the CB. If I know, my other thing is, if you know your moment, your required strength, your MU, right? MU must be less than or equal to your capacity. Well, if I got to increase that by CB, then just divide by CB and start looking for that moment capacity. So say I should really just put another page here. Right. Let's say I needed 500 kip feet, but I could say my CB is equal to 1.1 instead of 1. Well, I can divide how much I need by CB. So 500 kip feet divided by 1.1. I can go to my tables saying, hey, I only need 454 kip feet. Instead of really, I need 500, but I reduced how much I need because of the CB factor. I hope that makes sense, right? You can go to something that in the table might say, oh, it has 460 kip feet, which would be less than the 500. But if I get to multiply it by 1.1, then I have enough capacity. If that makes sense. So that's just how to incorporate the CB of not equal to 1 in your design. So let's summarize design of a flexural member. There are 3 limit states. One, full plastic yielding. Right? This is the entire cross section has yielded. Not just the onset of yielding of any element. 2, lateral torsional buckling. That's where my top flange, if we're looking at a W section, my top flange bows out and buckles. And then local buckling, so web or flange local buckling. If I'm doing design and I know my capacity that I need, which might be something that you have to calculate, right? I need to know, I guess what I need to know, right? My capacity that I need. I need to know my MU. Golly, gee, stop doing that. Okay, my MU, how much capacity I need. My yield stress, my material properties. My unbraced length, maybe that's given. Maybe I have to look at it and figure that out. And I need to know if I get to reduce my capacity by the CB factor. All right. MU, that's my required strength, how much I need. All right, this is my yield stress of the steel. Unbraced length, meaning unbraced length of the top flange, which will determine if you're in the plastic yielding section, the inelastic lateral torsional buckling, or the elastic lateral torsional buckling. That, right? That was that. Right. That chart. And then my modification factor for lateral torsional buckling for non-uniform moment along the length. The guiding, what I can use to guide my design in the spec is chapter F. Those have the actual design equations. And then in the manual, I have the design tables in part 3. Table 3-1 has the CB values. Table 3-2, I get to select by my plastic section modulus. That's it. Also, I can use if I want to calculate my design. If I want to calculate my capacity, provided Fy of 50 KSI and a CB of 1. Right. And then the plots, 3-10, Phoebe MN versus your unbraced length plots. If you know your unbraced length and you know your moment capacity, go find that. Go find the nearest solid line and call a day, right? So that is the end of flexural design. I'm going to leave some examples for us to do together if you would like. And then next, after this, we're going to do shear. Thanks.